Hello everyone, good to see you again. I call myself Mr. U.S. Patil, working as an assistant professor at Sharad Institute of Technology, College of Engineering, Edram, Ichalkanji, which is at Kolhapur district, Maharashtra. Today, we're going to see an example on finite element analysis. As we have gone through the principles of finite element analysis, introduction about finite element analysis, safe functions, boundary conditions. So on that basis, we'll go through an example on this finite element analysis. So we'll take one example here. The structure consists of two bars, an axial load of P equal to 200 kilonewton is loaded as shown in this figure. Determine the following: element stiffness matrices, global stiffness matrix, global load vectors, nodal displacement, stress in each bar, and reaction forces. So we'll see here the element stiffness matrix and all this whatever we need to find out and determine. So first step, we'll see that finite element, this is what we have converted it in element model, finite element model. This is, as you know, this is node 1, this is node 2, and this is node 3, and according to that we have taken this node 1, node 2, and node 3, and node 1 to node 2 this is element 1, and node 2 to node 3 this is element 2. So we know this displacement factor, that's d, that is equal to u1, u2, and u3 of matrices of transform matrices. So this is what a displacement of that particular nodes, and we know that the P is applying here. We'll see step by step now. The element stiffness matrix we can given. So this is one we know, we have know this equation that K1, that is for element 1, that is A1 E1 divided by L1 into the matrix of 1 minus 1 minus 1 and 1, and for 2 K2 for this element A2 E2 L2 matrices of 1 minus 1 minus 1 minus 1 1. So on this basis, the global stiffness matrix with assembled from K1 K2, from K1 and this K2 we can write like this. Here A1, K1 is A1, A1 is E, this is what A1 has been given 1000 and E1 is 200 GPa into 10 raised to 3 we can take, and 1000, right? Are you getting this? A1 is 1000 and E is 200 GPa. So A1 E1 means, as per A1 is 1000 and E is 200 into 10 raised to 3, and L1 is 200. L1 is this 200. So now we are here matrices of 1 minus 1 minus 1 and 1, and this is of node 1 to node 2. This is node 1 to node 2 of this element. Similarly K2, that is K2 is A2 E2 divided by L2 of matrix 1 minus 1 minus 1 and 1. So here A2 is here 2000 and E2 is 83 GPa. So 83 into 10 raised to 3 into 2000, or you can say 2000 into 83 into 10 raised to 3. So this is what K2 stiffness matrix of this 1 minus 1, 1 minus 1 and 1 of 2 to 3, node 2 to 3, this node 2 to 3 for this stiffness matrix. Now we know that this the degree of freedom for axial displacement of a particular uh, for this bar, we'll see here. Now if you see k1 and k2, k1 and k2, that k1, the k1 I can write like this in this matrix's form, that is a1 e1 divided by l1 minus a1 l1 e1 divided by l1 into 0. Why 0? Because we are considering 1 and 2 node, and this is first element, so this is 0 elements. And similarly for k2, this is we are taking 2 and 3, so 1 is here 0. Here 1 and 2 we are considering, so 3 is here, row and column is 0. Are you getting this? 1 and 2 we are taking 1 and 2 k1, and k2 is 2 to 3. So here k1 is 1 and 2, 1 and 2, and 3 is here 0. Here k2 is 2 and 3, 1 is here 0. If you we need to find of k, that is k1 plus k2. If you put the values a1 e1 divided by l1 over here, and if you add them together, so we'll get this matrix in this form, that is 10 minus 10, this is 0, and minus 10, 26.6, and minus 16.6, and 0 minus 16.6 and 16.6. This is what node 1, node 2, and node 3 when you club off the both the matrices, right? So now this is the structure of loaded by point force only. The global point load vector is given by, where if you see here, the force P is acting at that nodal point is 2. So you have to consider this node, and now is now we can say here, sorry, F 0 2000 0, this is at node 1, node 2, and node 3 where force is applying. So at this moment node 2 is force is acting to 200 kilonewton. So this is what 2000 of this 4. Yes, at this area force is acting where, on this area. How much is area? Is 2000 area. At that portion the force is applying, and where is 2000? On this node, this is second node. So this is what force 0 2000 and 0 transfer matrix. In the finite element equations are given by kd equal to f. So on that basis, if you see this, so k and the degree of freedom, that is u1 u2 and u3, that would be, this force is of 200 here. The known boundary conditions are, we know that u1 and u3 is 0 because it has been constrained, this has been constrained, so fixed. So only here if you say at node 1 u1, at node 2 u2, and at node 3 u3, here u1 and u3 is fixed, so there is no any kind of degree of freedom, so it has been constraints here. So here at node 2 u2 is with there, that would be a degree of freedom. So Here u1 and u2 is 0, and when known boundary conditions are applied and the elimination approach is used, so that is u1 and u3 should be eliminated. The finite element equation takes the following form. So 10 raised to 5, 26 into 6 into u2, that is equal to 10 raised to 3 into 200, and on this basis u2 equal to 0.0751 mm. So this is what degree of freedom or displacement of u2 we got here. Now from equation that b equal to dn divided by dx equal to 1 by l, that is minus 1 into 1, and stress, that is sigma equal to e b into u. So if you say sigma 1 equal to 200 into 10 raised to 3 into 1 divided by length of that first element is 200, and this is matrix of minus 1 into 1, and at node 2 displacement is 0.0751. So from this you can get a stress on that element 1. Yes, this is stresses on element 1. So now sigma 1 equal to 200 into 10 raised to 3 dn by dx, right? That's this is area, right? So now we can say here 200 into 10 raised to 3, 1 divided by length of that element, and matrix of minus 1 and 1, and here u1 and u2 because of element 1, 1 and 2 node. At node 2 the displacement is 0.0751. So now it would be 75.1 Newton per mm square. If you solve this, we will get 75.1 Newton per mm square. Similarly for sigma 2, that would be E is 83 into 10 raised to 3 into 10 raised to 3 divided by the length divided by length of the element 100, and matrix of minus 1 and 1, and node 2 to 3. So node 2 a displacement is here 0.0751 and u3 is 0. From this second element we got a stress value is minus 62.33 Newton per mm square, and the reaction forces R1 at the node 1 and R3 at the node 3 are obtained from the equation of like this: Ri equal to minus C of Ui minus Ai. So thus from the equation we can write in a such a form. So now we can get this value. So now 10 raised to minus 5, 10 minus 10 and 0 that we have got here, right? So now this is transfer matrix, sorry, that is transfer matrix 10 minus 10 and 0, and u1 u2 u3, yes, and minus 0, the A is 0, so we'll get this 75 kilonewton. The reaction is of element 1. For elemental 2, elemental 3, we have this 10 0 16 and 16.16 16.6. So now here 0 0.075 and 0 minus of 0, that is equal to minus 125 kilo Newton. So this is what the reaction what we are requiring, reaction forces at R1 and R3, right? So this is what one example on that bar element. If you want to make a finite element analysis in software, we'll see another problem of this particular steel bracket. If you see, for example, in 10.2, we say, or a second example, the structural analysis of steel support is shown in the figure 10.8, and this is a typical bracket used to support towel rods. The bracket is fixed at the screw holes. The bracket is loaded at one point in the center of the large hole. The load is 200 Newton. The load is 200 Newton, and the thickness of the bracket is the modulus of, sorry, the bracket is 3.125 mm, and determine the deformed shape in the software only, and thus modulus of the elasticity is E, that is 200 gigapascal, and Poisson's ratio is 0.3. So here we know this figure. On this basis we need to uh, go through a software procedures. So we'll see first, according to this, we'll see the procedures. The bracket is meshed with the solid 8 node plane stress element. By a plane stress element, we are assuming that there are no stresses in the thickness direction of the bracket. So this is one constraint or degree of freedom we have taken, and thus NSS software is used to solve this problem. So we need to follow this procedure. First, turn on the key point numbering functions in the analysis utility menu. Then create the key points to form the area that will become the bracket, and then they connect the key points with lines and define an area to form the bracket master area, and then fillet the lines to form the curve on the right side. Use fillet radius is of 0.1, and then create two area defined by the fillet curve and the respective corner of the bracket master area, and create the circle area in the center and the left side of the bracket. And if you see here, this is figure we are looking for, and create the circular area in the center and left side of the bracket. This is center and left of the bracket. Subtract the area defined by the fillet, the the center circle, and the two smaller circles to form the shape of the bracket intended to be analyzed. And then next step, add the two lines forming the bottom of the circle together to form one arc that encompasses the lower semicircle of the center circle. Define the material property of the steel, which kind of material you are going to make this part, and select that for steel. Select the elastic modulus and Poisson ratio are the important quantities for selected material which we have selected. Then define the element properties as called 8 node structural solid. In the element type window, set the option of setting the plane stresses to the thickness. If you want if you say that hint in the window it is the value of K3, we'll get over there. We'll see this in a software even. So just go through this procedure how it would be. So just go through, will particularly on the software we even look into that. And then set the real constants, set number to 1 and the real constant for the plane stress with a thickness up to 3.125. That has been you have set. The the bracket mesh the bracket which have taken the elements, and do so by picking the lines around the outer boundary of the bracket and setting the elements edge of length 0.0125, and the next set the element edge length around the small circles to the 0.00125, then mesh the area. Apply boundary conditions. We need to set the boundary condition, that would be structural displacement on the degree of the screw equal to 0 and structural force or movement of the on the bottom of the large circle equal to 900 Newton in the y direction. And the solve all this above in the software and list the nodal results of the solution with respect to all degree of freedom. Once you plot the nodal solution with respect to all the degree of freedom and show both the deformed and undeformed shape of the bracket as well. If you all done this procedure, if you go through the software analysis, you will get modal solution per node like this: node 1 2 3 4 5 6 7 8 9 10 etc. So many plenty of nodes you have created on that bracket like this. See, so many nodes are there and so many elements are there. So we have given such kind of procedure and we have followed the procedure, and it goes in such kind of procedures in software. So this is what the following are the degree of freedom resulting area in the global coordinates. So this is ux, the displacement and x direction, displacement y direction, and displacement in z direction. We have constraint in the z direction, given the degree of freedom in z direction is we have put 0. So this is constraint 1, z direction. So we are not allowed to any movement in a z direction. And this is x, u and y direction. These are the displacement values. So once you have done this nodal displacement results, so you will get these kind of figure where deformed and undeformed shapes will get to know as. This is what this is deformed shape, and see here little bit a deformed shape. So on that basis software we come to know that this is a deformed, and this will see a practical step by step in a next practical session. Okay, and this is what an one example and one procedure in a software on the basis of finite element analysis. So next video we'll see the another topic. Thank you one and all.